Hello everyone, my name is Amit. Today, I will be discussing a new benchmark to evaluate uncertainty estimation in long-form generation using deterministic ground truth. Despite the widespread use of LLMs, they are still prone to mistakes. For example, consider a system that supports initial patient assessment and decision-making. A mistaken output could cause unnecessary suffering or delay critical treatment. To trust such AI systems, we would want models to assess their own confidence, much like humans do. And ideally, this confidence should be calibrated. Imagine a large repository generated by an LLM, say Cloud Code. In such long generation, some mistakes are very likely to appear, even if there are only a few. But should a few isolated mistakes make us label the entire generation as incorrect? This is why we believe correctness should be defined at a finer resolution than the full generation. Suppose we ask a model to tell us about the movie Titanic, and this is one possible output. How do we evaluate whether this output is correct? Even if we have a ground truth answer from Wikipedia, is it the only possible ground truth? Clearly not. The same facts can be expressed in countless different ways, and therefore we do not even have a single ground truth to compare against in the first place. But even if we had a single ground truth, the problem would still not be easy. Remember, we want to evaluate correctness at a final resolution, but splitting the text into atomic units and matching atoms between the model output and the ground truth is already a hard task by itself, even before we discuss correctness. We may find that some atoms in the ground truth were not addressed by the model at all. Is omitted information the same kind of error as stating wrong information? Some mistake can be found by directly comparing the generation to the ground truth, but some claims cannot really be verified. Are they correct, irrelevant, or hallucinated? The bottom line is that evaluating correctness in free-form generation is hard. Almost every attempt in the literature to evaluate free-form correctness either introduces noise or misses the exact target we actually care about. To address these challenges, we introduce SALT, Single Answer Atomic Long-Form Target. In SALT, each task algorithm generates both the question and its unique long-form answer. Because the ground truth, answer decomposition, and comparison are deterministic, we can evaluate correctness without LLM judges or expert annotation, given as noise-free labels. This also lets us evaluate correctness and uncertainty at fine resolution over atomic units. SALT include 8 automatically generated tasks, making it scalable, controllable, and harder to memorize for future models. Let's take the matrix multiplication task from SALT as an example. If we evaluate the output matrix as a whole, it is simply wrong, 0% correctness. But with fine-grained evaluation at the line or element levels, we get a more accurate view of correctness, confidence ranking, and calibration. SALT decomposes outputs into sequential, verifiable units, allowing us to monitor correctness at a high resolution as the generation unfolds. Using this capability, we show that long-form correctness strongly depends on the correctness of the answer prefix. Better prefix lead to more accurate future units. We also find that global prefix correctness has a stronger effect than local prefix correctness. Lang effects, however, are observed too, however, are relatively bounded. When testing the model confidence ranking at different evaluation granularities, we find that models struggle with individual atom ranking, but show reliability at coarser granularities. This highlights the need for confidence functions optimized for high-resolution units. Finally, we identify a reasoning trade-off, where reasoning mechanisms such as chain of thought or specialized reasoning training boost accuracy and calibration, but systematically degrade confidence ranking, making models less able to distinguish their own errors as they become more convincing. This were only a fraction. Read the paper to find out more about confidence function and which function performed the best, calibration as the generation unfolds, and calibration at different granularities, and why do we even need zero noise benchmark for accurate uncertainty estimation to begin with? And there are much more. Thank you.